Okay, so for this week, I will be substituting Shai. So for today and Friday. And I will continue with the course. So I think the goal was, so to continue the course, the goal was prove that finite classes are learnable, or agnostic learnable. And the main tool will be uniform convergence. But I will have a little bit of review here to make sure that you remember all the stuff needed. So I think actually these are the two main concepts in the whole course. So the definition of PAC learnability is the most, I think, the single most important concept in the whole learning theory. Once you understand what it is, then you will be fine. So it will, all problems, most of them are built around that. And the main tool to proving results about PAC learnability is uniform convergence. So I will talk about this today. So let me have a short review on what PAC, agnostic PAC learnability was for a hypothesis class. So I will denote usually H. You know, H is a hypothesis class. And this is the domain set. So a hypothesis, a hypothesis in our hypothesis class is just a labeling function over the domain. And we can view agnostic learning as a game between a tester and a learner that tries to learn something. So I have one tester here, and I have one learner. So let me put it a little bit far here. So let me fix some hypothesis class here. So fix the domain set X and hypothesis class H. Now the tester picks some epsilon and delta. Each of them are between 0 and 1, and says that I want you, the learner, to be epsilon accurate most of the time. And by most of the time, I mean with probability at least 1 minus delta. So that's the requirement, our requirement from the learner. And we will give epsilon and delta to the learner. Now the learner says that I can do it, just give me enough instances, labeled instances. So assume that he has some sample complexity in his mind, so the number of samples he needs. So he has a function, he passes back to the learner the number of samples, to the tester, sorry, the number of samples he needs. Then the tester So it's important to see that here the learner doesn't know anything about the distribution, just knows about the hypothesis class and that how much it should be accurate. And then the tester, she decides which distribution to use to, challenge the learner. So she can pick anything. So let's say picks D, distribution over the labeled, over the domain and 0 and 1. Okay, picks it. Then in the next step, she draws some sample of size M from that distribution IID and gives it back to the learner, right? So S is given to the learner. Now, the learner should have some algorithm to, output some hypothesis based on the examples that he has seen. So assume that we have some algorithm here that takes, the sample and outputs one hypothesis, usually one of those in the hypothesis class. And then says, okay, that's my choice. And now the tester should test it. How can she test it? We say that, checks for agnostic case, compares it to the best hypothesis in the class. So LD of H minus LD of H star should be, test if he fails. So if it is larger than epsilon. And by H star, I mean, the best hypothesis in our class with respect to the true distribution. So because she has access to the distribution, she can compare it to the best one possible and see if the learner failed or not. So if we do this, if we draw samples and test the learner, sometimes it fails. The error will be more than epsilon. Sometimes, the difference between the best possible thing will be more than epsilon. Sometimes it will not fail. And now we count the number of times that it failed. So this is a probabilistic procedure because the sample is drawn, randomly. If we do it multiple times, sometimes it's successful, sometimes it's not. So with respect to this distribution, the question is that how often the learner is successful. So how often learner or fails. So is it more than delta? If it is, then it was not a good learner. It was not because that was the requirement. So the probability that here we say how often is with respect to the distribution that the tester picked. And it should work if for every distribution and for every epsilon delta in this range it works, then we say that, okay, this was a true agnostic learner with sample complexity M and with the algorithm A. So there is such algorithm. So if only one algorithm exists, we say that it's learnable. So that's, I think, the main concept that we are working here. Yeah.
Just a question. So when you said that the algorithm A, from the learner, chooses a hypothesis that is usually in the hypothesis class, what do you mean by that? What does usually mean there?
Okay. You know, the main thing here is that we compare ourselves with the best hypothesis in the class. Okay, that's the main use of H. So I didn't talk whether, so sometimes it can give some, I mean by usually. Okay, so in the standard setting, maybe we require that H is in H, capital H. So we require that the learner outputs a labeling in our class. And it's called, I think, proper learning. So there's a term for it. And there are non-proper cases where it can output any labeling that he wants, but it will again be compared against the best one in H. So that's non-proper learning. So both of them have similar characteristics. I don't know if Shai will tell you about you, but the main difference is about computational complexity, but not sample complexity usually, at least usually in the standard case. Okay, that's usually. Okay, so any questions about this one? So that's the main concept. And now we want to see which hypothesis classes are PAC learnable, by which I mean there exists a good algorithm that can learn them. Okay. So how can we prove something about sample complexity of this? There are two kinds of bounds that people acquire for these problems. One are lower bounds and one are upper bounds. For lower bounds, you want to prove that the number of samples you need is at least this. So you want to show that for all algorithm, no one can beat this sample complexity. That's a little bit hard maybe. For upper bound, you just need to find one algorithm that has a small sample complexity and can learn successfully. So one strategy to prove that finite hypothesis classes are agnostic PAC learnable is to choose a certain algorithm and then prove that its sample complexity is small. So what kind of algorithm is natural here? I think you have heard in the class maybe. So what kind of algorithm do you suggest here that we use? Any?
Go through all H, pick the best one with respect to sample.
Yes, exactly. So that's the ERM algorithm, right? So suggestion or prove an upper bound for sample complexity of a specific algorithm namely ERM, which the algorithm does, finds the best hypothesis in our class with respect to sample. Yes. So I have something missing here. So how can I write it? So I think A as of S, the output is some hypothesis, right? So this is some hypothesis. And I want to say that I'm looking for the best hypothesis. So if I compute the loss of this one, it will output. So it's a little bit inaccurate, but I think it gives the idea. So I'm looking, yeah.
Change your D subscript to an S, and then you're not taking the min over A of S. A of S just has this one function.
Yes, you are right. Yes, you are right. So I'm wrong here. So I'm yes, so it works on the sample, not on the distribution. Sorry. Thank you. Maybe I need to use the notes. And how can we bound the sample complexity of ERM? So one intuition, I think, is that because ERM works on the sample, not the true distribution, it will work well when the true loss is very close to the empirical loss. If that is the case, then because this one minimizes the empirical loss, it will automatically minimize the true loss as well. Then it will be a good learner, right? So one thing that we require, so I think that it will help, is that the empirical and the true errors will be similar. So in order to formalize this kind of idea, I think I need a new column. So definition, epsilon representative samples. So I will say that S is epsilon representative with respect to H. And you can put other things with respect to H and domain and the loss function and the distribution mainly. When for every H in H, for all hypotheses, the true error is similar to the empirical error on the sample. So if we have such sample, it means intuitively that if we just minimize the loss over sample, we will automatically approximately optimize LD as well. So we will be looking at how can we find epsilon representative, or how many examples do I need to make sure that it is epsilon representative. And so I won't use that word, I think. So let me add one lemma here. So to make sure that this intuition works, so if S is epsilon representative, then the ERM algorithm will work well on that, by which I mean the ERM algorithm, I will superscript it by ERM. So the ERM algorithm.
Is that with respect to HX epsilon, or what's the index?
This is S. This one?
No, with respect to HX something in D.
This is the loss function. So if usually we fix 0, 1 loss in this course, So it's not that important, but the main things are H and D. Okay. So yes, it's that's like this loss. So if we have a epsilon representative sample, then the ERM algorithm will work well. I mean, if we give the ERM just that sample, then the loss of this thing will be close to the loss of the best hypothesis. And by close, I mean 2 epsilon, not epsilon. So again, I use the notation of H star, by which I mean the best hypothesis in the class, not just for the class. So that is why epsilon representative samples are good for ERM to work. And so let's not remove this one, but here we will have the proof. So because it's epsilon representative, then LD and LS are similar. So LD of anything, including the output of ERM, will be smaller than LS of that plus epsilon. That's due to the definition of epsilon representative sample. And also LD of H star will be larger here than LS of H star plus epsilon. So because it's epsilon representative and in the definition we had absolute value, we have both upper and lower bounds. I mean, LD and LS are very close, so we can use it as a lower bound or upper bound. Both cases will work. So using these two, we can combine them together to say that LD of ERM of S minus LD of H star is smaller than, you can substitute LS here. Plus epsilon minus LS of H star, again plus epsilon. So let me put this epsilon here. So now we know that because this is the best, what does ERM do? It will work on the sample, finds the best hypothesis on the sample, right? So on the sample, the loss of ERM is good. It's all the time less than or equal to the loss of anything else on the sample. So this will be smaller than epsilon, so the whole thing will be less than 2 epsilon. So any questions about here? Okay. So now we have proved that the only thing that I need is that we have an epsilon representative sample. Then the best algorithm is not the best. A working algorithm is ERM. So how can I prove that if I have a large enough sample, it will be epsilon representative? So intuition is that, if you have many samples, you have covered many, situations, and it's similar to having the whole information about the distribution. But how can we formalize that? So okay, so that's where the definition of uniform convergence comes. So, but let me define the sample complexity of uniform convergence. So with respect to some h. So I put some superscript here to denote not the usual sample complexity, but the sample complexity of uniform convergence. So again, I have some parameters, epsilon and delta. And so define it like this. The minimum number such that for every distribution D, if we pick a sample of size, so let me define it, the minimum number m such that for every distribution D, if we pick a sample of size m, then with high probability, with probability at least at least 1 minus delta, S is epsilon representative. So I think this is a very important definition. So, but it's related to what we wanted here. So we wanted to have large enough samples to make sure that it is epsilon representative. And this defines the same thing. How many samples do I need to make sure that I am epsilon representative? But there is also one confidence parameter, because even if you have many, many samples, could be the case that just in a very few, sometimes you have one sample that is not epsilon representative. You don't want to say that it's not, this thing is not working. You want to say if it most of the time it works, then it's okay. So you have one other definition here. And so how is this sample complexity related to the sample complexity of agnostic learning? Do you think, do you have any idea about that? So if I prove something about this, how can I use it for proving something about the original problem. Yeah.
Would it be greater or equal than any m from, because it's for every distribution, right? Whereas for agnostic, it's for one distribution.
Yes, yes. But we should be a little bit more careful because the parameters may not exactly match. So, yes. So, we need to use the lemma that we proved here to relate them, right? And we saw that there is a factor of 2 somewhere, so they are not necessarily exactly the same. So, also, there is another difference. So we can, based on this lemma, we can somehow say that if we have uniform convergence, then we have agnostic learning. Because if we have uniform convergence, then ERM will work based on this. So again, if we have, let me write it down. So if informally, if we have enough samples for uniform convergence, then with high probability, let me write it down. Then with high probability, our sample S is epsilon representative. Then, based on this, and based on the lemma, we know that ERM will work in that situation. When we have an epsilon representative sample, then ERM is good on that. And because ERM works, we have found one algorithm that works. It's sufficient for proving upper bounds for agnostic learning. So it will be agnostic PAC learnable. Here I have just one color, I think. So to summarize this, and to be more accurate, I will write the sample complexity of agnostic learning is all the time less than the sample complexity of uniform convergence, but for a different parameter. So that's a corollary, maybe. And the intuition is clear, right? Why, anyone knows why this is epsilon over to not 2 epsilon? It could be 2 epsilon, right? Because there's 2 here. Yeah.
Well, yeah, because of that too. I mean, you want to bound the error by epsilon. So if you didn't have epsilon over 2, you bound it by 2 epsilon. So
Yes. Yes, exactly. So the lemma says that if you are epsilon uniform convergent or epsilon representative, then you have error of 2. So in order to have error of epsilon, you need to be epsilon over 2 representative. So I could write it from the beginning that if I'm epsilon over 2 representative, then I will have error of epsilon. So here, in order to get an error of epsilon, you need to be, the uniform convergence needs to work on a smaller error threshold. So it's tougher. And it's just an upper bound. We didn't prove anything about the converse. We don't know about the other direction yet. Because we just looked at one simple algorithm, ERM. Maybe in future we will find out better algorithm that work better than ERM with a smaller sample complexity, which will not be the case actually, but it's still open. Okay, so now we will go to the technical part of the proof. In order to upper bound the sample complexity for this one, we can instead upper bound the sample complexity for the other one. So So I think Shai had taught part of this before, but this part is a little bit new, so I will be slower a little bit. So let's define the new goal. So the new goal is to find upper bound for So we are mainly, for this session, we will prove results for case where this hypothesis class is finite. Just like the proof that we had for realizable case. In that case, we proved something based on union bound. And proved that all finite hypothesis classes in the realizable case are learnable. But can we prove something similar for agnostic setup? So the way that we prove it will be similar to that in a sense that they both use union bound. But we need one more technical tool here. So in order to prove that, so let's have some a strategy to attack this problem. So if you see, we have two problems inside this problem. So I will write the strategy in 2 steps. So step 1. For a single hypothesis, how many samples do I need to make sure that for just a single hypothesis, the true error is close to the empirical error. Because the epsilon representative definition work with all of the hypotheses in the class. So in order to prove that, I need to show that all of the hypotheses in the class, for them, the empirical is close to the true. So let's start with just one hypothesis right now. So for the first step, we want to prove that for a single hypothesis, the true error will be close to the empirical error if I have enough instances, samples. Bound the number of samples to make sure that LD of H is almost LS of H with high probability. So that will be the first step, proving that for a single one, we have a bound for sample complexity. And the second step will be to combine all these. You know, we have a bound for this hypothesis. We have a bound for the other hypothesis. So, and we want that for all of them together, the true error is close to the empirical error. So assume that we have just two hypotheses in our class. What can we do? For example, 1% of the time this one fails. 1% of the time this one fails. By which I mean that its true error is not close to its empirical error. So 1% of the time this one fails. 1% of the time this one fails. I can say that at most 2% of the time one of them fails. So this is a union bound, right? We say that because the probability that one of them fails is less than the probability of this one fails plus the probability of this one fails. That's the idea for the second step. Use union bound to bound the probability that one of them or any of them fails. Yes?
So in this proof, do we assume that for every epsilon we can find a sample so that this is epsilon representative, or what do we assume?
For the first step or for the general question?
For general proof, like what do we know about that?
So for the general proof, we are trying to say that how many samples do I need to make sure that my sample is epsilon representative with high probability? So that's the question. And the meaning of this is that how many samples do I need to make sure that for all hypotheses in my class, the true error is close to the empirical error. So first, I will say that what about the case where I have just one hypothesis basically in my class, and I want to make sure that its true error is close to its empirical error? Then I will extend the result to the case where I have multiple hypotheses in the class, and I want them to be close to their true error at the same time.
I think the case that you can never achieve epsilon limit.
Yes.
So how do you deal with that?
So this is a strategy to attack the problem. It might not work. If it works, it shows that it was not the case, right? So if we can bound this step and bound that step in a good way, then it shows that we could find actually an epsilon representative, and there exists. It actually shows that there exists such example, such representative.
For instance, for the coin flip, we proved that if the best function has error of 1/2. So that's, we can't find a sample which is a quarter representative for that function.
Okay, that's a good question. So it doesn't mean that we cannot find. Okay. So in agnostic setting,
So we're comparing it to the best function, right?
we compare ourselves to the best function. So what is the best function for coin flip? So we have, yeah,
So
so
if we have like something close to 1/2, you're going to be good, right?
yes,
Agnostic learning.
yes,
But
yes.
step 1 says for a single function, we're trying to bound the error.
Not error. Yes, maybe I'm wrong. So I want to bound, to say that these two things are close to each other. I don't want to say that this one is close to 0. Or I don't want to say that any of them is close to 0.
So LS would be close to 1/2.
Yeah, both of them could be half. Exactly. Good. So if you think the realizable case, the agnostic case is very, very more natural. Because in realizable case, we have two assumptions together. One is that the error, it's not a coin flip. The error will always be 0. The best hypothesis has error 0. So that's the first assumption. So it doesn't have a probabilistic nature. The problem is deterministic. That's the first assumption. And the second assumption is that not only it is deterministic, but also a hypothesis in our limited set of hypotheses in the class will work. So it is deterministic, and one hypothesis in the class can work perfectly on that. So there are two very, strict assumptions that are not very natural. So that's why we went to agnostic setup, where you compare yourself to the best one. Okay, so that's the strategy to deal with that. So let's start with the step 1. Any questions here? So for the first step, we are trying to say that the average of some variable on some small sample is close to average on the true distribution. Because when we compute the loss on a LS, it's just loss average over the sample, right? So we need a statistical tool that says that when you want to compute the averages of some variable, you are not aware of the true average, if you just take a few examples and average them, then it will be a good estimation of the true average. It's a very basic statistical question, and it's very important. It's the main tool here. So they are called concentration inequalities. So one of them that we use here is Hoeffding's inequality. So let's have some random variable. So let's assume that we have some kind of, IID random variable. So they could be the result of coin flips, or so sometimes they're head, or maybe a more continuous version, the height of a building, different buildings, or different things. So, but they are the important thing is that they are IID from the same distribution. So because they are IID, they have the same mean. So they have the same mean because they're IID. And we have one more additional assumption that is very important. That take values in AB. So basically, we are assuming that they are bounded. They could not be infinitely large. So if you have a Gaussian distribution, so it's not bounded. Sometimes it can give you a sample, far apart. It's not bounded. But here, for this inequality, I'm assuming that the random variable is all the time bounded between A and B. Then that's the main result. Then the empirical average is close to the sample average. So I can write the true error is close to the empirical average. True average and empirical average are close. So let's put some epsilon here. Because it has a probabilistic nature. I cannot bound that the difference between these two things is all the time less than epsilon or greater than less than epsilon. So let's start with the false thing. So something about the m, it could be a function of m, say that if I have enough samples, then these two will be close, epsilon close. I cannot prove it because it has a probabilistic nature. Every other time, maybe there could be one possible sample that the average is far apart from the true. So if you have a distribution like this, the average is here. You generate some examples, and the average will be close to its true value. But sometimes, maybe out of luck, you generate some examples that are apart in one way, in the right section. Then your average will not be accurate at all. So you cannot say that my true average and empirical average are close, but you can say that with high probability they are close. So that's why we always have these probabilistic things. So the probability that they are far is small. The probability that this one happens is small. So I don't remember the bound here. Yes. So it's 2 e to the b minus a squared. So you will not be required to prove this, I think. But you can use it as a concentration inequality. One good thing about this inequality is that it's exponential. I mean, the probability will be exponentially low when m is large. So if we have many examples, the probability will be very, very small. The probability of failing. So that's a good thing. So it's a very powerful inequality. Sometimes they are polynomial. This time is exponential. It's very good. OK, so how can we use this to prove our first step? So we can say that probability that LD of S minus LS of H so that's the quantity. So fix some H. So for a single hypothesis, I want to say that its true error is close to its empirical error. That's what I wanted here because of this thing. And now I can use this inequality here. It's about the average of things, so I can rewrite this as an average. So it is equal to the probability that so the true error is just the expectation over the distribution of what? Of the loss. So that's the loss of H and Z. So Z coming from the distribution minus 1 over m. This is the sample size. Z in S of L H Z. I just wrote the definitions of LD and LS here. As you see, I have one average, but average of losses. Those losses, who knows, can we have a bound here for losses? Do we know similar thing about the smallest and largest value that they can? Yep.
We usually take 0, 1.
0, 1. So we in a binary classification, we assume that error is 0 and 1, between 0 and 1. So I'm trying to work with some random variables between 0 and 1. I have one empirical average of them and the true average of them. So I can simply use this inequality. So based on Hoeffding inequality, I can say that it's less than 2 to the e to the minus 2m epsilon 2. But b and a are 1 and 0. So it will be just this. So that's the probability of failing in one single hypothesis. So the next step is to generalize it to all hypotheses in the class. And use union bound to prove that. So we can say that the probability, so let's write proof of the main result. The probability of failing is small. We want to bound the probability of failing. And what is the probability of failing? It fails when our sample is not epsilon representative, right? So our goal was to bound. Our goal was to say that if I have enough instances, then my sample set is epsilon representative. That was the goal. In that case, I will have ERM working. So the probability that S is not epsilon representative. So we can rewrite it like this. There exists one H in H such that LD of H minus LS of H is greater than epsilon. That's the definition of epsilon representative. So to be more accurate, let's write H here. Is not epsilon representative with respect to H. Right? So I just wrote the definition. So somehow I have proved it for a single one now, but I have many of hypotheses. What can I do here? I use union bound. So the probability that one of them fails is at most the sum of probability of that one of them fails. So here we can write based on union bound, it's less than the sigma over all hypotheses in the class, the probability that LD is far apart from LS. That's the union bound. So the left hand side is again smaller than, based on Hoeffding equality, Hoeffding's inequality says that the probability of failing one of them is smaller than 2 to the 2 to e minus 2. 2m epsilon 2. So it's a constant thing. It doesn't depend on h anymore. So it's just a sum of the same things. So how many things do I have here? It's just h times 2 to the e minus 2 epsilon 2. Okay, so what did we do here? We proved that the probability that my sample is not epsilon representative is small. So with high probability, it is actually epsilon representative. When we have a finite class. So what can we say about the uniform convergence sample complexity? So I have bound the probability of error, but I have not yet come up with some bound for the sample complexity. How can I reuse this to find a bound for sample complexity? Any suggestions? Okay, so it means what is the definition of sample complexity? It means that how many samples do I need to make sure that with probability at least 1 minus delta, error is less than epsilon. So yes?
So MH of epsilon, this thing is
Is
M.
what?
M.
So how can I write it in terms of epsilon and delta? So I need a way.
Take log.
Log of what?
Log of this, shift A to the other side, take log and we can do it.
Yes, exactly. So how can I start, I mean? Yeah, we can do it. But what is the first inequality that I write? Then I will continue with log, exactly. So yes?
You write less than or equal to 1 minus delta after that?
Here? 1 minus delta? So that's the probability of failing. So could be this one is better, right? So let's write it here. So we want that the probability of error, not error, that failing to be less than delta. This is the requirement of the problem. The sample complexity should be that large, M should be large enough that this thing becomes small, such that we have this property, that this is a small. So now we can do the log and division. So that's E minus 2m epsilon 2 less than delta over 2h. That's, we can take minus 2 m epsilon 2 is less than h. Next step, if we, because it's negative, it will reverse the thing, and so it will be m should be larger than ln of delta over 2h over 2 epsilon 2. So there is a negative here. Let's write it instead of negative, we can rearrange this. So that's basically the sample complexity of uniform convergence. So we are quite there. We bounded the sample complexity of uniform convergence. So the last corollary is about the sample complexity of agnostic PAC learning. Any questions here? Yes?
Our premise for finite age, wouldn't exactly the same thing work for countable age?
Sorry?
So wouldn't exactly the same proof work for countable hypothesis class age? Because you could just take the bound the first by a half and a quarter, then you get power series.
So the problem, assume that we have natural numbers. You know, the countable could be, is equivalent to something like natural numbers, right? So for natural numbers, we have infinite number of numbers in them. And this size will not work. It will be infinite. And this.
We can bypass that by bounding the first by half, the error by half of the original error, whatever it is.
Half of the hypothesis?
Yeah. So we have here independent hypotheses, right? And we bound each one. And then we say, okay, then the error is less than the sum of all of them, right? But we don't have to bound each one by the same amount. We can bound the first one by half, and by a quarter, and by 1/8. Then we're gonna still get the same thing.
But because we have infinite number of them, you know, even the half of infinite hypothesis class is another infinite class, okay? So
We can bound each independently.
you can bound for, you know, assume that you want to do it for an infinite hypothesis class. So let's. So I have some hypothesis class infinite, which is like, you know, h1, h2, hn, and it keeps going. So I can bound the probability that this one fails. I mean, its true error is not close to its empirical. This one, this one, this one. So, but when I have infinite many of them, the bound will be useless because it will be times an infinite number.
We can make each error be less than 1 over 2 to the power of
infinite. So there will be some infinite in the. So you want to make sure that this one is very, very, very close to its empirical. The probability is very, very.
H1 is less than epsilon, H2 is less than epsilon over 2, H3 is less than epsilon over 8 percent epsilon, and so on.
So the last one will require infinite. And also the thing that we needed to prove was not that. We wanted uniform convergence. So one question is that where does this name come from, right? Uniform convergence means uniformly for all hypotheses in the class. We want that for all of them we have the same epsilon. That's one thing to be able to use our proof. The second thing is that if you do that, the last one will require infinite number because epsilon will tend to be to 0. The last one in the infinite needs many. There was a question? Yeah.
So weren't we looking for bound for PAC learnable that was epsilon over 2?
Yes, exactly. So we can use this for bounding the PAC, agnostic PAC learning, right? That was your question. So let's write it quickly, yes. So the corollary, good. The sample complexity of agnostic is just, you know, ln of 2h over delta. Now here I can substitute it. I should substitute with epsilon over 2. So there will be a 4 and 2 and 2. So there is a 2 here. Exactly. So any other questions? Okay, so thank you. For the next session, I will talk about no free lunch theorem, which is a very fundamental result, and a negative result to say that if we don't have enough examples, we cannot learn, and some classes are not learnable, actually.